x equal 1.5. Then, as usual, we can check the lines we created. So in general display, here you can deselect all of the faces. I'll just select the plate and the lines, all the lines of the perpendicular one and this center line. So there you have. This is how it should look like. So we are along the center line. We need only the wall shear stress to calculate the skin friction coefficient. Instead, along these perpendicular lines, we need the velocity distributions. But also, so we are asked also to show the distribution of k, epsilon, omega, and nu t. So you can do that in plot, xy plot. Here I typically select node values. I order points, even though I'm not going to write them. The x-axis in this case, so if I want to plot the perpendicular values to the plate, is z1, x0. So I'm changing the plot direction coordinates or vector. Then you can find the turbulence properties in instead of pressure we go to turbulence, and here you can see turbulence kinetic energy, turbulence dissipation rate, epsilon. For this case you don't have omega, because for the K epsilon model you are not solving omega, and so we can plot them, for example, to show how they look for all the lines perpendicular to the wall.
It's kinetic energy, right?
So for example, the turbulence kinetic energy,
Kinetic energy, yes.
this is how it looks like. So it increases as we are moving along the plate, or at least it's increasing its width, but it's decreasing its maximum value at the wall. And then also epsilon, you can say plot. Here it is not really nice to, doesn't look nice. I think we need to use the logarithm log scale option for the y axis. So if you go in axis on the bottom here, you can find here, we can select axis y and set log and apply. So there now it looks a little bit better how the epsilon distribution is shown in and now deselect the log, apply, and I'm showing also the
Where did you select the axis option?
yeah, in axis, then axis y and log. Then finally, I can show the turbulent viscosity. This is not nu t, this is mu t, so it's dynamic viscosity. There is a factor of rho, but basically the same shape since rho is constant. So we can show turbulent viscosity distribution. Then I can show you also how to do that for the k omega. So let's see what we can find in the k omega. So if you read data k omega, that file, for the same XY plot that we created. Now we can also check the what is wrong here. Maybe I'll just read both case and data. Okay, omega. Okay, I did a big mistake now because I cancelled all the surfaces I created with the lines. Okay, I'll do it quickly. I'll recreate all the lines. Every time you create a line, then you can save your case, so then it stays there. Now I didn't. The mistake that I didn't save the case, so when I loaded the previous case, it's all the saved settings are lost. Okay, so let's see for the k omega what we can find. Now it looks better. So in turbulence, for the k omega, you can see that you have all of the k, epsilon, and also the omega. So also the epsilon is available when you are solving for the k omega. So let's plot, for example, omega. I need to change the plot direction. Also in this case, I need the log for the y value. So that's how the omega looks, which is the specific dissipation rate. Let's also look at the epsilon, if now it looks better, yes. And so you can compare the results you obtain with the k omega in the epsilon model and also with the two different grids. And okay, we can move to the second part. So to calculate the skin friction coefficients as a function of Reynolds theta and the log wall. So for that we need again to save basically two quantities that are the wall shear stress so the wall shear stress that you can find still in the XY plot, wall axis. Yes.
So, can you show once again what you've done with the axis for putting the epsilon? I know something else.
You mean to use the log?
Yeah.
So this is for k x. So for the k omega, now I'm the k omega case and data. If I select the turbulent dissipation rate, you want to use a log scale, so you should go in this, you should hit this axis on the bottom, and then just select axis Y and select the log option and apply. So then when you save plot, the Y axis here is log. Was this the question? Or
Yeah.
and you can do that both for epsilon but also for omega, for the omega model. So that also this makes like some kind of sense. It's not just like overlapping lines, curves. Okay, so then we can save our files. Let's start with velocity. The velocity distributions at the different x coordinates. So we are going to plot or to write these files for. Let's first plot these velocities so let's see how they look like. Now I'll disable the log. So these are the velocity distribution, and we can save them in. I can do that in separate files. So just select one by one each line for different axes, and I select to write to file, and I can write the. For example, this is let's call it 0.1 dot xy or just 01.xy. So in that file I'll get me my velocity distribution for the line at x equal to 0.1. Then I select the next line, line 0.2. I can write 0.2 or 02.xy. And then do the same also for all the other lines, so that I have separate velocity files. The next thing we can do is to plot the wall shear stress. So we can select, instead of velocity, we go in a y-axis function, we select the wall fluxes, this wall shear stress. So let's check. I need to deselect write to file. Let's first plot it. And I need also to change the plot direction vector, because this is x equal to 1 and z equal to 0. And I'll plot it along my center line. So that's how it looks.
What are you writing now? Wall shear stress?
Yeah.
For all the lines together, or?
No, only for the center line. The one that is parallel to the plate. So for the k omega, which is the one that I'm post-processing right now, it should look like this. Then you can select write to file and write it to another XY file. So that let's call it tau underscore w dot xy. So these are the variables that we need to solve to post-process, let's say, to answer for the problem. So then we can open an Excel file. If you have a previous Excel file for the previous homework, then it's you can basically just copy paste the new values in the cells of the previous Excel file, because the formulas are the same. So the same formulas that we used for the previous homeworks are this one. So then just copy paste, then it's automatic. I can show you now how to do it from scratch. So then we go, first I'll copy paste the wall shear stress, and also all the velocity profiles at different x coordinates. Okay, so I have all of them here. Then I can cancel, I can delete the first column of the velocity profile starting from x equal to 0.2, because this is the same for all of the velocity magnitude. So I can just delete this one. So I can also delete this white column, so that I get so right here the x coordinate. This is for the first column of the wall shear stress file, and this is tau wall shear stress. Then this is instead our y. This is from the wall, and here instead we have the velocity at 0.1, velocity at 0.2, v at 0.4, 0.6, at 1, and at 1.5. So I delete also the first 3 rows. And so these are the files that these are the values that I need to post-process. We can start by calculating okay, let's write here different x values. So 0.1, 0.2, 0.4, 6, 1, and 1.5. Then here we can get u infinite. The u infinite is we can calculate like the maximum value, so the max of the column relative to the x coordinate. So for 0.1, we select this column of the velocities, of the velocity distribution, and we get the maximum value. And then you can just pull this also for the other x coordinates. Then I can get the rho infinite. This is almost constant. we can plot it in the, for example, in the contours in Fluent if you want to check the value there, or maybe the plot even, or the contour. So the contour you have is density, contours of density. You can see that this is constant to 1.17. This is for the same for all the x coordinates. Then we also have mu infinite, so the dynamic viscosity. Also, this variable we can plot it, for example, as a contour in Fluent. So contours of properties and molecular viscosity. And that's equal to 1.79 times 10 to the power minus 5.
For the rho infinity, what is the formula?
For the rho infinite, this is constant. Because we are calculating rho using the ideal gas equation of state, but the pressure temperature variation in the domain are minimum. So that $79. Okay, so these quantities are for Reynolds theta. We need theta. To calculate theta, we need to solve this integral. We solve it by the summation, the calculated summation of the different delta theta for the different cells in the boundary layer. So we need to calculate delta theta again for different value of the x coordinate. So delta theta is the ratio between uy over u infinite. So the uy, we define uy has the algebraic average between the two velocities for our data points. So this value plus the next value over 2 over u infinite, that for x equal to 0.1. We multiply that by 1 minus the same average value of the velocity. So I copy paste this value in here, multiplied by dy. So the difference between the second point, so the largest one, minus the previous one. I'm missing here the brackets. Okay. So this is the formula to calculate the theta. We can add some dollars here so that we can lock the u infinite. We need to lock it in the vertical direction. So we can lock the number. We put that dollar before the 3. I'm missing also u infinite here. The 1 minus uy over u infinite. And then we can lock instead the horizontal directions of the letter for the y, so that we can pull them without changing the column for the y. And then I can just pull this in horizontal and then in the vertical direction. Up to the previous, not to the last one, but the previous last one, the before last one, the data point.
Can you show the formula one more?
Yep. So that's the arithmetic average of the two velocity at the two data points. Then over M3, U infinite, 1 minus again the arithmetic average over U infinite times delta y, so the difference between the largest y distance from the wall of the data point minus the smaller one. Let's check the, if I set this one, I'm getting the correct values here.
There's some book in my-
Is different results of something wrong Alright, so once we have delta theta, we just find theta for each x coordinate. So this is the, we use the sum function in Excel to sum the values of the columns for all of the x coordinates. So now we have theta, we can calculate Reynolds theta. So this is rho infinite times U infinite times theta over mu infinite. And we pull this also for the other x coordinates. So there you see that the Reynolds theta is equal to 10,000 at x equal to 1.5, which is then the value that we need to, at which we need to plot the law of the wall. But before that, we still need to calculate the wall screen friction coefficient. So we first get tau wall. So for tau wall, we need to get the correct value of tau wall for each x value. So the first one, we go looking for x equals 0.1, or the closest one to x equals 0.1, and we get the corresponding tau wall value. And we do that for also for x equals 0.2. X equals 0.4, x equals 0.6. X equal to 1. And finally x equal 1.5. So there you have the tau wall for each x coordinates. So we can calculate the wall skin friction coefficient CF according to the formula shown there on the whiteboard. So this is equal to the ratio between tau wall over 0.5 times rho infinite times u infinite at the power of 2. And we can pull this also to the other x direction. And now we can insert a chart to plot the CF as a function of the Reynolds theta. So we select Reynolds theta, CF, and then you get this kind of distribution that you can compare with the values given here in the website. So this is the first point. The second point is the calculation of the law of the wall at Reynolds theta equal to 10,000. So that means at x coordinate equal to 1.5 approximately. So first of all, we can calculate the friction velocity u tau. And this is the square root of the wall shear stress over the density at the wall. In this case, this is constant, so it's equal to the rho infinite. And we can just pull this up to the x equal to 1.5. Which is the value that we need. So this u tau is going to be the one that we are going to use to calculate our y plus and u plus value. So I'm going to create some new columns here for y. Let's also create it for u, so the one that the velocity that we are going to use, y plus and u plus. So the y column vector is, or with the array, and then the vector is the distance from the wall, so these values of the line perpendicular to the wall. We copy paste that vector. For u, we need to get the velocity distribution perpendicular to the plate at the x equal to 1.5, where our Reynolds theta is equal to 10,000. So we select this column, copy, paste it here. So now we can calculate y plus according to the equation shown in the whiteboard. So this is equal to y times u tau. We're going to take u tau for x equal to 1.5 over new wall. We don't have new, we have the dynamic viscosity, mu infinite. So we need to divide mu infinite by rho. So this is going to be our mu, our kinematic viscosity. And we can lock here, or I select this for x equal to 0.1, maybe just select them, even though they are constant for the correct value in x equal 1.5. And we can lock all the u tau and viscosity and density values, because we don't need to pull them. And then we can calculate also u plus, so this is going to be equal to the ratio between u over u tau. And we can lock also u tau. And if I pull both of these, I'll get my y plus u plus distribution, and I can plot it in a chart. So my x value is going to be the y plus, and my y value will be the u plus value.
Sorry, if I may ask. So I wasn't, it wasn't clear for me what you should submit as a report. So I want the report. Is the Excel file what you actually want for there?
You can write like a Word or PDF also, where you can explain a little bit more how the.
Okay. So I wanted to submit both, but it just allows one file.
Okay.
So you can make it maybe two, like if you want to submit this and or.
Yes. I mean, I suggest you to write like a PDF file, because also I don't know if Tim already mentioned about the project, what the project is, but it's basically you are going to need the simulations also, because in the project you are going to simulate all the cases with all the turbulence model and describe also the models. So if you do it like right now for the homework, it's let's say ready for the project. So then
Okay,
you
thank
can-
you so much. Then it's better.
It's, yeah, it's,
Okay.
there is not much extra work then for the project.
Okay, that's fine.
And so this is the of the wall. Then we can set this x axis to a logarithmic scale, and you should get something like this. And this was done for the k omega, the standard k omega model. So you should do this for also for the k epsilon model. So basically, for the same grid, you can just copy paste the new values of tau wall and velocity distribution instead of these columns. When you are changing the grid, you should be careful that, of course, these equations are valid for a certain number of points. So in this case, we were using 156 points. So you are going to have probably more points because the number of grid points is higher. And also, you should then be careful about the tau wall value that you are going to select here, because this was selected, let's say, manually, that we're going through the X array to find the correct matching value. So then you should be careful that you are selecting the correct one. All right, so there are no questions.